Okay. So internal energy of a gas. Okay, so now we are talking about the whole gas, right? Not just one molecule. Okay, so earlier for one molecule we have written that if you have U for one molecule, then it is F by 2 kBT. I'm just writing it here so that we don't have to go back and check it again. So this is for a molecule, or one molecule of ideal gas. Now let's say you are doing this for a mole, for 1 mole, okay, right, for 1 mole of ideal gas. Now 1 mole is how many molecules? 1 mole is how many molecules? Waiting for you all. 1 mole is how many molecules? Very good. Avogadro number, right? That is, for 1 mole you'd have Na multiplied by F by 2 Kb, right? This step clear? Okay, another thing to note here is, see, I'm not writing average now. The reason I'm not writing average is, just like we had it earlier, when you are finding it for one single molecule, because everything has a different speed, different kinetic energy and all that, this is an average. But now when we do it for 1 mole, which is lots of molecules, right, Avogadro number of molecules, we don't need to find, we are not finding it for a single molecule. What we are doing is we are finding this for an entire mole. So it's like finding the total number of pens that that all the students in a class has, right? I hope you remember that analogy where we found the average number of pens for one student, right, and now we are finding it for everyone together, right, total number of pens that all the students have. So we don't need to write average here. Now what is Na into Kb? Hopefully you remember, Na into Kb is R, so this shall become, shall become F by 2. Na Kb is R, so into T. So this is for 1 mole again. So this is for what? For 1 mole of gas. For 1 mole of ideal gas. We are only talking about ideal gas. We are not even going to worry about real gases in physics, right? Chemistry માં તોય તમારે થોડુંક આવ્યું છે, physics માં એવું બહુ કંઈ આપણે ટેન્શન લેવાની જરૂર નથી. Okay, so this is for 1 mole of ideal gas. Now the next thing, instead of 1 mole, if you have it for mu moles, right? Okay, for mu moles of ideal gas, you have U equal to F by 2 mu RT. This step clear? If anyone wishes that I explain it, you can put it in the chat box. Okay, if I get enough requests, I will do it. Okay, fine. So that's the internal energy of what? Ideal gas. Don't forget what we have found. This is the internal energy of an ideal gas, right? What is mu? Mu is number of moles, F is degrees of freedom, R and T you know very well. Okay, so that's the formula of internal energy. Warning, do not use it, do not use for liquids, solids or anything else. Okay, use it only for ideal gas. Okay, big warning this one. નહીતર એક ટાઈપના ક્વેશ્ચનમાં કન્ફ્યુઝન ક્રિએટ થવાનો પૂરેપૂરો ચાન્સ. Okay, now this is for an ideal gas, so let's convert this formula to another form. Okay, so formula is U equal to F by 2 mu RT. Now from ideal gas equation, PV equal to nRT or mu RT. Okay, if you write n for number of moles, no problem. PV equal to mu RT. Okay. So if we use that here, I have another formula. I have another formula for internal energy of an ideal gas. Did you understand this derivation? One step derivation here. Okay, mu RT is equal to P into V. P into V, that is pressure into volume, right? So this is another formula for internal energy of an ideal gas, right? U equal to F by 2 P into V, that is pressure into volume. Okay, right? Now, okay, so based on this, we can now find out internal energies of different kinds of gases. So let's just try a simple example. Suppose I give you a question as find internal energy of 3 moles of oxygen, of ideal oxygen gas. Okay, moles of ideal oxygen gas at 27 degrees Celsius. Come on, can you do this? Hurry up, hurry up. Hopefully you all remember R's value, it is 8.314, okay, in SI unit. પણ જ્યારે કેલ્ક્યુલેટર ન હોય ને 25/3 લઈ લેવાનું. Okay, don't worry, you can take R's value as 25/3. you can check 25/3 એટલે 8.33 જેવું તો આવશે. Okay, so it's fairly close to the correct value. ચલો ચલો જલ્દી કરો, waiting for the answer. Hurry up, hurry up. Done. Okay, so I've got some answers. Units to લખો. Got some answers here. Fine, I'm doing it now. Let's see whether you got it right or not. Very simple question. First of all, oxygen gas. Which kind of molecule? Monoatomic, diatomic, rigid or diatomic non-rigid? Which one? Which one? O2 તો બરાબર. Monoatomic, diatomic, rigid or diatomic non-rigid? Diatomic માં બે છે હો, જોજો. Diatomic માં બે છે ને. You have to decide which one. Diatomic rigid or diatomic non-rigid? Diatomic rigid. Very good. Okay. So diatomic rigid or ideal. Ideal કેન એટલે diatomic એટલે rigid જ છે. Simple. So here we get U equal to diatomic rigid. What is the value of F? 5. So 5/2 mu RT. Okay, this step clear everyone? U equal to F by 2 mu RT. So F equal to 5. બરાબર ને? બસ ખાલી હવે વેલ્યુઝ મૂકવાની હતી. So 5/2, 3, R is 25/3, 8.314 લો તો થોડોક અલગ આન્સર આવશે. Temperature 300 Kelvin. Okay, so 3 cancelled, and here you get 5 into 25 is 125 into 3, 37500 by 2. This answer will be in joule. So this is going to be 1. મારે તો અલગ આવે તમે કહેતા 18 કેવું આવે 750. ના ના બરાબર તમે આ જ કીધું હતું 18750 જૂલ. Okay, right? If you would have taken 8.314, you get a slightly different answer. No problem with that. In short, you can say that this is 1.88 kilojoule. No, sorry, not kilojoule, into 10 raised to 4. 1.88 into 10 raised to 4 joule. Fine. So this is about internal energy. Now let's go to a textbook question. This question number is 7 from exercise. Question 7 from exercise. Its second part. Okay, its second part. We haven't done it, right? First part એ બાકી છે ને કે નથી? હા બાકી જ છે, બધું બાકી છે. Sorry, first part. Okay, so what's the question? Estimate the average thermal energy. હવે આ કંઈક નવું આવ્યું. What is meaning of thermal energy? અરે thermal energy એટલે કંઈ નહીં, energy due to random motion, that is called thermal energy. Okay, energy due to random motion is called thermal energy. આને કંઈ ન કહેવાય, આને internal energy કહેવાય. Okay, this is nothing but internal energy here. So first question, find the average thermal energy, means internal energy of a helium atom. See, for a single atom, right? So single atom formula for internal energy is F by 2 kBT, right? Okay, so let's put value. Now which atom is it? Helium. Helium atom કઈ દીધું છે? મોનો એટોમિક. So degree of freedom 3 by 2, kb 1.38 into 10 raised to minus 23, and into temperature, right? Yes, temperature. First question, temperature 27 degrees Celsius means 300 Kelvin. Okay, first one clear? First question. Right? બસ તો આવી રીતે સેકન્ડ અને થર્ડ કરી નાખજો. Right? So that is your homework. Okay, make sure you do the second and third on your own. Right? Now that's about internal energy of a gas, right? Now see that when these molecules, let's go to the next topic, when these molecules move around here and there, they're definitely going to collide, right? Sure, you understand, and we have already talked about that. So now we go over and concentrate about onto the collisions, right? So therein we are going to study about something called mean free path. Okay, mean free path. And along with that, simultaneously, when we derive things, we will also be deriving something called collision frequency, and we will also derive something called relaxation time. Okay, these all things are connected to each other. એટલે એવું નથી કે ત્રણ ડેરિવેશન છે. Most of the steps are same, and then one step here or there you get some other quantity. So we are going to derive three things here: mean free path, collision frequency, and relaxation time. Okay, right? So let's begin. First of all, what is the meaning of these terms? Okay, what is the meaning of these terms? Let's write that. Very simple meaning है. Okay, first of all, mean free path. Okay, now I think in your book the symbol is either, well, lambda or sigma. I don't exactly remember which of these. Anyway, let's write lambda. Okay, here, so mean free path, I'm going to use the symbol lambda, right? what is the meaning of mean free path? Mean એટલે average. Okay, so તમારી બુકમાં L છે, કંઈ વાંધો નહીં. L is actually a very confusing symbol, don't you think? L તો આપણે કેટલી બધી જગ્યાએ લઈએ. Let's use lambda. Okay, so average of free path. What is this free path? Right? It's that, do you remember that molecules continuously are moving in random directions in a vessel? Do you all remember that? Right? So mean free path is as follows: average distance traveled by a molecule between two successive collisions. Successive collisions means one after the other. So what this means is, between two collisions, on an average, how much distance does a molecule travel? એટલે એકવાર ભટકાય પછી બીજી વાર ભટકાય, એ બે વચ્ચે કેટલું ડિસ્ટન્સ એ કવર કરે, that is called mean free path. Okay, meaning clear? પહેલા ત્રણેય ડેફિનેશન લખાવી દઉં, પછી એકવાર એનિમેશન જોઈ લઈએ. હોપફુલી things will be much easier that way, right? So second definition, so this is about how much distance it travels between two collisions. See, you will have to imagine molecules and atoms flying around, okay, in your room. It is change, don't forget, you are living by breathing oxygen gas, right? And air definitely has lots of molecules roaming here and there. So try to imagine, try to think what's going to happen after collision. It will go in some other direction, then it will hit again. Okay, so that's mean free path. Next, collision frequency. Collision frequency, આ થોડું easy છે સમજવું, નથી નામ જોઈને ખબર પડી ગયું એવું નથી લાગતું. Let's call it FC for collision frequency, right? It is the number of collisions experienced by a molecule, number of collisions experienced by a molecule in unit time. For example, let's say that unit time is 1 second. So what we are finding is, in 1 second this molecule will collide how many times? જેટલી વાર collision થાય એટલી વાર direction change થશે. યાદ આવે છે આવું? So in 1 second or in some unit time, how many collisions will be there of this molecule, okay, of a particular molecule? See, here also actually it's a kind of average, because every molecule is going to behave differently. Random motion hoy એટલે બધા molecule નું behavior exactly same no hoy, right? So I recommend that for complete understanding we add the word average here also. Yes, speed will change, no problem, right? Speed ને બધું change થશે, speed, direction, but that's fine. એટલે તો સ્પીડ ની આપણે એવરેજ ને RMS ને એવું બધું લઈએ છીએ. Okay, so things are going to change. So I said that we need to take average here also, or we need to say that it's an average, because a molecule is not going to, all the molecules don't have the same collision frequency. Some will have less, some will have more. એ બધું જ random હોય. Okay, next, relaxation time. એમાંય તે ખરેખર average આવે. Okay, બધામાં average આવવાનું જ છે. Average relaxation time. Okay, what does this mean? લખાવી દઉં, વર્ડ અઘરો છે, મીનિંગ એકદમ સિમ્પલ છે. The time passed or time interval between two successive collisions of a molecule is called relaxation time. Meaning clear or not clear? બે વાર કોલિઝન થાય ને એની વચ્ચે કેટલો ટાઈમ લાગે, that is in what time will the next collision occur, that is called relaxation time. The symbol of relaxation time is tau. Okay, the symbol of relaxation time or average relaxation time is tau. I know confusing, પણ હવે એટલું બધું ફિઝિક્સ છે, એટલા બધા સિમ્બોલ્સ છે, રિપીટ તો કરવા જ પડશે, નહીતર ચાઇનીઝ શીખવાની તૈયારી રાખો. Okay, so relaxation time symbol is tau and it means that after one collision occurs, in how much time will the next collision occur for a particular molecule. Okay, બીજાના નહીં, બીજાનું તો ઘણું બધું ચાલતું હોય. For this one molecule, after how much time will the next collision occur. એમાંય તે એવરેજ હોય, કારણ કે એવું હોય કે એવું ફિક્સ નથી કે એક કોલિઝન થાય પછી આટલા ટાઈમ પછી બીજું કોલિઝન થાય. ઓકે, થિંગ્સ આર રેન્ડમ, સો ઇટ્સ પોસિબલ દેટ collision number 2 occurs very quickly after collision 1, and then it might take a slightly longer time for the next collision. So that's why we have to take an average, right? Also, it will not be same for all the different molecules. For some molecules it will be less, some it will be more, and some it would be in the middle, kind of an average. એટલે એવું બધું ચાલતું હોય, right? Okay, is there any relation between mean free path and relaxation time? Yes, absolutely. There is a very close relation between all these three things, right? Between all the three that we have written here. એટલે જ તો કહું છું, ડેરિવેશન કેવું છે કે 10 સ્ટેપનું ડેરિવેશન હોય ને તો 9 સ્ટેપ સેમ હોય ને પછી એક સ્ટેપમાં ખાલી જરાક અલગ કરવાનું એટલે બીજું આવે. ઓકે, so they are very closely linked with each other, these three quantities, right? So let's head over to the animation first of all, right, and then we will derive. એટલે પહેલા એક વખત માઇન્ડમાં બધું પ્લે થવા માંડે ને, તમને દેખાવા માંડે ને કે હા આવું હોય, right, then it is easy to derive. Just wait for I'm preparing everything. Okay, wait. Okay, can you see the screen? See the animation here? Fine, let's start. So this is just the same thing that I did show you before a few classes, right? So here we are going to concentrate on this particular molecule, right? Okay, and I'm going to give this molecule a name. The name is very apt. It's funny, but it's absolutely true, right? This molecule, we are going to call it dawn. Okay, so dawn is this molecule which we are going to observe, right? And wherever dawn moves, we are going to see a white line so that we know where it's going, right? Okay, we are keeping a watch on dawn. Okay, so let's begin. I've slowed this down too much so that you get a chance to see what's going on. Okay, the red one is not in consideration. Please ignore the red one. Okay, don't have a look at this, right? Just ignore this. Focus on this one, right? So let's This is still very fast. Okay. So what we have here is that now this molecule is moving away and it's going to hit something, right? Okay. So there it's going to, hopefully it will hit that. No, it missed. Nasibo. Okay, it hits here, right? Do you see the direction changes? It hits here. Okay or not okay? Over here, right? Now you see after that collision it has started traveling a distance, right? After that collision it has started traveling a distance in a straight line, right? Obviously it will move in a straight line, right, until some force will act on it, right? That is until the next collision. Okay, here it's hitting with the wall, right? But for our discussion you should remember that this animation is not true in 100% sense, because in reality there are too many molecules. So actually you can just say that it's going to hit the other molecule. You understand what I'm saying? Yeah, like this. Did you see this? I repeat what I was marking here. Do you see this molecule came in like this, dawn came in like this, it hits here, and now dawn goes off in this direction and hits here. Understood? Clear or not clear? Okay, and then it goes here. So do you see that this is the distance between two collisions? Do you see that this is the distance traveled between two collisions? Okay, so every time that distance is going to be different. You see, every time that distance is going to be different. Let me show you an example of that. You see, have a look at this one, all the way from here. Check a corner thi check અહીંયા સુધી આવે. You understand what I said? That free path is very big. Similarly, from here to here, from this corner to this corner, short. Once again, from this corner all the way till here, right? So it's a big free path. So every time the distance traveled between two collisions, it's not the same. એટલું તો સમજાઈ ગયું ને? Every time the distance traveled between two collisions is not the same. Look at this graph also, that will give you an idea. Sometimes it travels more distance between two collisions and sometimes it travels less distance between two collisions. Clear? And hence the average, right? That's why we have to take average. કોઈક વાર વધારે distance travel થાય, કોઈક વાર ઓછું થાય. That's why we are taking average and we are calling it mean free path. Name clear? Mean free path. Okay, then the next thing, relaxation time સમજાવી દો. You see, it would definitely have taken some time. Listen to this carefully. It would definitely, this molecule dawn, right? This is dawn, don't forget, dawn is making white light. Dawn would have taken some time to travel from here to here, correct? Right? So that time, the time it takes from here to here, that time is nothing but relaxation time. Clear? That time is nothing but relaxation time. If you want, you can read the definition again. It is the time between two successive collisions of a single molecule. Relaxation time clear? And now we talk about collision frequency. Now how easy છે. Relaxation time સમજાઈ ગયું હોય. Collision frequency tough nothing. So here we go. It's that let's play this animation for like 1 second. Okay, so આપણે જોશું 1 સેકન્ડમાં કેટલી વાર collision થાય. That is called collision frequency, and we'll watch it carefully and we'll see in 1 second how many collisions it makes, right? So let's play. Chalo, 1 2 3 4 5 6 એવી રીતે કાઉન્ટ કરવાનું, સમજ પડે કે નહીં? Okay, so in a unit time how many collisions it would make, that would be collision frequency. Meaning clear? Okay, right? So that's it about the that's it about the three definitions, right? They're extremely closely linked with each other. Okay, now coming back to board. So let's start deriving them. Now you see, when we derive, we have to make a few assumptions. First of all, we are going to assume that each molecule is an incompressible sphere, of diameter d and radius r if you want, okay, and radius r, but generally we tend to write this in form of diameter, okay, right? Incompressible kone kehvaય? Something whose size never changes, right? Something whose size never changes. The other thing is, because we are finding a kind of average of everything, right? Average. Gases are compressible. मैं यहाँ gas નથી લખ્યું. Read this carefully. I am saying molecule is incompressible. બેમાં ફરક છે ને. Gases are compressible because there is a lot of empty space between molecules, but molecules themselves are incompressible. Clear? Okay, so so I was saying that because we are going to take averages of for finding all these quantities, we will start with considering that let each molecule move with the RMS speed, which is a good kind of average. Remember, we took RMS speed, okay, based on the idea that kinetic energy, when we take the average kinetic energy, the speed becomes RMS speed. એવું મેં derive કરાવ્યું હતું તમને, short વાળું derivation. So that's why we are going to assume that each molecule has how much speed? Speed equal to VRMS. Okay, and any formula તો તમને યાદ જ હશે, under root 3kBT by small m. Okay, hopefully you remember that. So keep this in mind, right? Keep this in. Now let's draw. Okay, drawing is very important here because the diagram reveals all the secret. So let's say that this is dawn. Okay, let's say that this is dawn. Now dawn is moving in this direction with how much speed? VRMS speed, right? With speed VRMS. So let's say that dawn just completed one collision. Listen to this carefully. Let's say that dawn just completed one collision and now is moving in this direction, and let's say that dawn reaches till here. Dawn reaches till here. Okay, dawn reaches till here. So suppose dawn traveled some distance L. Suppose dawn traveled some distance L. Okay, and here, or lambda actually, and here made a collision, and here made the next collision. Did you understand what I said? Basically, Don moved from point A to point B and made the next collision. Clear or not clear? At A, Don had collided with something else. So Don moved in this direction. Right now, Don is moving in this direction. Ultimately, when Don reaches B, okay, when Don reaches B, it makes the next collision. So આ બે વચ્ચેનું distance, average distance શું થાય? Mean free path. Clear so far? Yes or no? No સમજાણું? આમાં શું ન સમજાણું? મને તો એ ન ખબર પડી. એકવાર collision અહીંયા થયું હતું. This is where it had first collision. And now this is where it has second collision. તો એ બે વચ્ચે કેટલું distance travel થાય એને શું કહેવાય? બરાબર ને? Okay? So it hits like that. હવે આ ડાયાગ્રામમાં તમે મને આટલું બધું લખાવડાવ્યું ને એટલે આ ડાયાગ્રામ હવે બગડી ગયો. We'll have to draw a new one. Okay? So again, here is Don and it's going to move from A to B. So Don is going to hit other molecules. Don ni dadagiri chhe. Okay, Don is going to hit other molecules, right? Listen to this carefully. Don will hit other molecules whose center comes anywhere, not just between these yellow lines. Listen to this carefully. Not just between these yellow lines, but also any molecule whose center comes within these green lines. You understand why? I am saying that Don is going to hit any other molecule whose center comes within these green lines. જો draw કરીએ એટલે વધુ સમજાશે. Suppose a molecule is here. બધા મોલિક્યુલનું રેડિયસ ડાયામીટર સેમ છે. આ તો ડાયાગ્રામ ડ્રો કરવામાં નાનું મોટું થાય. એક્સક્યુઝ મી ફોર ધેટ. આને તો હિટ થશે. યસ ઓર નો? Yes or no? આટલું તો સમજાણું ને? If the center is on this yellow line, it will definitely hit. Okay, but that's not the point. હજી આગળ કહું છું. Suppose the center is even on this line such that this distance is equal to radius. સમજ પડે છે? Such that this distance is equal to radius. Then also they are just going to brush or touch each other. Yes or no? Clear or not clear? આ જ્યારે આમ જશે, okay? So what's going to happen here? It's that the center of any other molecule, listen to this carefully. Let me just write it, okay? તમે હું બોલીશ પણ તમે લખશો નહીં તો તમને નહીં ખબર પડે. So I am writing it here. This molecule, સારું લાગે એટલે this molecule કહું છો, બાકી તમે સમજી લેજો whom are we talking about. So this molecule will collide with any other molecule whose center comes within a distance of 2r, that is equal to d. Okay, 2r or equal to d from its center. Did you understand this line? Its એટલે whose center? From Don's center. Okay, એવું લખી જ દો અહીંયા. This sentence clear? નહીં, નો સમજાણો? અહીંથી અહીંયા સુધી ડિસ્ટન્સ કેટલું થાય? 2r થાય ને, તો એની વચ્ચે ગમે ત્યાં કોઈ આવશે ને સેન્ટર, આનું સેન્ટર અહીંયા આવવું જોઈએ તો એને હિટ થઈ જાય. ઇફ સેન્ટર ઇઝ બિયોન્ડ ધેટ, if center is beyond that, it will not hit. Do you realize why? Okay, so if the center is anywhere between these green lines, the center is anywhere between these green lines, it's going to hit, right? Okay, one more thing, you know, on paper this looks like lines. Okay, on paper this looks like lines, but molecule to sphere hoy, a molecule is like a sphere. So in reality this drawing should be drawn in this manner. Watch this carefully, it's slightly tricky to understand what is going on. અહીંયા એક આવું સિલિન્ડર જેવું બને. Can you imagine the cylinder? Can you imagine the cylinder? Right? Also there will be not just green lines, but there will be a green cylinder. Did you understand the green cylinder, everybody? Okay, હવે હું તમારી સામે નથી, there is not much I can help you with this animation really. Okay, અને આવું animation કરવું tough છે. Okay, try to imagine what we are saying. It's like a ball is moving. Now this ball is going to hit any other ball whose center comes anywhere within this cylinder. Suppose બીજો ball હોય એનું center અહીંયા બહાર આવશે તો વાંધો નહીં આવે, these two will not touch, right? But if that center is within the cylinder, તો ભટકાઈ જશે, આમ જશે ત્યારે. સિલિન્ડરની અંદર સિલિન્ડર હીટ કેવી રીતે થાય? What are you saying, Nandini? Cylinder has double radius. Yes, you have to imagine hollow cylinder. Exactly, this is a hollow cylinder, right? Okay, remember it's imaginary. આવું કોઈ સિલિન્ડર હોય જ નહીં, પહેલી વાત. That's the key thing to understand. હા, એટલે આ એકય સિલિન્ડર છે જ નહીં. Yes, if the center of the other molecule is on that, then also it's going to touch. અહીંયા touch થઈને જશે. I hope that makes sense, right? Tangential આવશે. There will be a collision, but that will be completely tangential, right? It's like having a negligible effect. એટલે એ એની border છે, એના સુધીમાં કંઈ પણ આવશે તો એને touch થઈને તો જશે, right? Okay, so if that other ball or other sphere might enter this, no, it will not change direction due to touching, કારણ કે touching માં negligible force લાગે. Okay, so we can safely consider that it's as if it's not touched, પણ તો એને collision તો કહેવાય જ, right? Okay, so this is what Dawn is doing. Dawn is very evil, right? You can see એ ખાલી પોતાના સિલિન્ડર જેટલું આટલું જ બ્લોક નથી કરવાની ટ્રાય કરતો. Dawn tries to block double. You understand what I'm saying? Dawn doesn't just block a radius r, it actually tries to block a radius 2r. Yes. Okay, Ami, the answer to your question is yes. Other molecules should be close to Dawn for collision, right? એટલે બીજો મોલિક્યુલ ગમે ત્યાં હોય ને એનું સેન્ટર આ સિલિન્ડરની અંદર આવી જાય ને તો આ બે ભટકાઈ જશે. ધેટ્સ ધ કી થિંગ. આ રેડિયસ એવી રીતે આવે છે. ઓકે, ઇફ ધ સેન્ટર ઓફ ધ સેકન્ડ વન ઇઝ આઉટસાઇડ દેન દેર ઇઝ નો કોલિઝન. ઇફ ધ સેન્ટર ઇઝ ઇનસાઇડ દેન દેર વિલ બી કોલિઝન. જ્યારે અહીંથી આમ જશે ને ત્યારે એને હિટ થશે. ઓકે, there is one more question. Let me answer that, then we'll proceed. Any other gas molecules can enter that imaginary cylinder without hitting Dawn. Well, see, Resha, here what we are considering is that for simplicity, this is a good thing. Here લખી જ નાખું. Here for simplicity, we consider other molecules to be equally spreaded or uniformly spreaded in the volume, right? Also we consider them to be stationary. Okay, so first one here, this shouldn't be a lot of problem. We are saying that the molecules of the gas, they are uniformly spread out in the volume. In the volume એટલે suppose તમારા રૂમમાં gas છે, air છે, તો એની અંદર બધા molecules uniformly distributed છે. Okay, first assumption clear? It is reasonable assumption, બરાબર ને? એવું તો છે નહીં કે એક જ જગ્યાએ બધા મોલિક્યુલ ભેગા થઈ ગયા છે અને ડાયરો કરતા હોય તમારી જેમ. ઓકે, so they are uniformly distributed. The second thing, this one would be a little strange. We are considering the molecules to be stationary. Dawn is moving, there is no doubt about that. Dawn is moving, but we are considering the other molecules to be stationary. Is that true? No. હું પોતે જ કહું છું. It's an assumption. Right? Why are we considering that? હવે તમને સમજાઈ જ જશે અને તમે માની લેશો એટલે તમે અગ્રી કરી દેશો, હા સર બરાબર છે. You see, what would happen if you consider others to be moving? તો હું તમને એક simple example આપું. Let's say Dawn starts from this point A and Dawn is moving in this direction. At that time, some other molecule, and suppose બીજા કલરમાં ડ્રો કરીએ, at that time some other molecule is here, but that molecule is moving in this direction. Then do you realize that this situation is very complicated, because here we cannot decide whether they will collide or not. સમજ પડે છે? સમજ પડે કે નહીં? It is a very complicated situation. રાઈટ, અને આમાં કેટલા બધા ફેક્ટર આવી જાય. એંગલ ડિપેન્ડ કરે, બરાબર, આ ડિસ્ટન્સ બે વચ્ચે શું છે એ ડિપેન્ડ કરે. રાઈટ, ફર્ધર હજી આ તો કંઈ નથી. ડુ યુ રિમેમ્બર વોટ આઈ ટોલ્ડ યુ ઇઝ દેટ મોલિક્યુલ્સ ડોન્ટ હેવ અ પ્રોપર પ્રિડિક્ટેબલ સ્પીડ. યાદ છે, બધી રેન્ડમ સ્પીડ હોય. તો આની સ્પીડ એ શું હોય ખબર નહીં ને આની એ ખબર નહીં એકચ્યુઅલમાં. then this is a tremendously complicated situation, right? So એવું નથી કે એવું નો કરી શકાય. રિમેમ્બર, with lots of complicated maths it can be done and it has been done. તમારી બુકમાં વેલ્યુ આપેલી છે, મેથડ નહીં. ફરી વાર કહું છું, તમારી બુકમાં ફાઇનલ ડેરિવેશન કરીને આપ્યું છે, મેથડ નથી દેખાડી. ઓફકોર્સ ઇટ ઇઝ રિઝનેબલ, બરાબર. મને ખબર છે મેથડ ઘણી મોટી છે, રાઈટ. દેટ ઇઝ અબાઉટ 2 pages of derivation with lots of integration and that also complicated one. So that part has been skipped and it is okay. એટલું બધું મેથ્સ તમે ખાલી ખોટું હેન્ડલ કરી શકો નહીં. Okay, there is no need. So here we are deriving a simpler version. Okay, we are deriving a simpler version where instead of all molecules moving, we are assuming that only dawn moves and others are stationary. સમજાઈ ગયું assumption? Again, this assumption is only to avoid the mathematical complexity. બાકી તમને ખબર તો પડી ગઈ હશે કે કેવું ખતરનાક થઈ જાય. Okay, so let's continue now once these assumptions are clear in your mind. So here, listen to this. Basically what this means is dawn is going to hit anything that comes within this cylinder. તો આ સિલિન્ડરનું વોલ્યુમ ફાઇન્ડ કરી નાખીએ. ઓકે, લેટ્સ ફાઇન્ડ ધ વોલ્યુમ ઓફ ધીસ સિલિન્ડર. V ઇક્વલ ટુ શું આવશે? પાઈ r સ્ક્વેર. ઓકે, એન્ડ ડિસ્ટન્સ h કે લેમ્ડા આવશે. અહીંયા લેમ્ડા લખવાનું, સમજાણું કે નહીં? આ ડિસ્ટન્સ કેટલું હતું? લેમ્ડા હતું. જો ફિગર્સ તમારી નોટબુકમાં, આ સમજાણું? લુક એટ ધ પ્રીવિયસ ડાયાગ્રામ. ડ્રો કર્યા છે ને કે નથી ડ્રો કર્યા? અહીંયા જો this distance is L equal to lambda. Okay, in that much time it's going to make the second collision, right? એટલે આપણે distance find કરવું છે. So volume V is equal to pi radius square lambda. Now look at this cylinder. આ cylinder નું radius r નથી, 2r છે. Did you understand? Or d, 2r or d for diameter. Got it? Yes, no? This is the radius of this green cylinder. Okay, that is d. 2r equal to d. So બસ હવે આ વોલ્યુમ અહીંયા લઈ આવો. So now I am going to write it as follows. Thus, in traveling a distance lambda, which is nothing but mean free path, traveling a distance lambda which is mean free path, this molecule, again this molecule is just a simple name, we know its true name, right, will hit with other molecules within volume V equal to pi d squared lambda. Clear? It will hit other molecules within volume pi d squared lambda. જે ઓલું ઉપર લખ્યું હતું એ જ અહીંયા લખ્યું, રાઈટ? એની અંદર જે પણ હશે એને હિટ થઈ જશે. So now that brings us to the next thing. How many molecules are there? Other molecules, barabar, right? Other molecules, but how many molecules are there, right? Okay, the number of collisions of Dawn for this molecule, that is Dawn again, equal to number of molecules within this volume. એટલે આ વોલ્યુમમાં જેટલા મોલિક્યુલ્સ હોય ને એટલાની સાથે કોલિઝન કરી શકે, રાઈટ? whatever is the number of molecules in that volume, that is the number of collisions of Dawn. એટલાની સાથે ભટકાઈ જશે, right? So how many these are, that's what we will find out the next time. Okay, we have run out of time. I repeat, it's that whatever number of molecules are there in that particular volume, Dawn is going to hit those, Dawn is going to strike or collide with those. But how many molecules are there? Equation no answer આપણે હજી આપ્યો નથી, right? So we will find it out the next time, right? How many molecules are there in that volume. Okay, so that's it then. Continue with it the next time, right? Goodbye.